So our last skill in learning Unit 4 on aqueous chemistry is on oxidation-reduction reactions. So this might be a new skill for many of you. So there's a couple parts that we'll go through to kind of understand what oxidation-reduction reactions are. So oxidation-reduction reactions involve the movement of electrons from one reactant who has a lesser attraction for electrons to another. So essentially, it's the trading or swapping of electrons. And maybe if you've learned about this before, you fall into one of these camps, either the Leo-Ger camp, Leo the lion says Lur, Leo the lion says Ger. And this really is just an acronym to help us remember that if something loses electrons, it's oxidized, gains electrons, it's reduced. Or maybe you're of the oil rig kind of camp, where oxidation is loss of electrons, and that's actually, we should have this underlined here. The I is really oxidation is loss, and reduction is gain. That's where the oil rig comes from. So however you want to remember it, it is important that we understand when something is oxidized, it loses electrons. When it's reduced, it gains electrons. So that's sort of some of the big pieces there. So this kind of little infographic summarizes this. Again, transfer of electrons is what a redox reaction is. So if something loses electrons, it's oxidized. Gains electrons, it's reduced. We'll see on the next page this terminology about oxidizing and reducing agents. And then we'll explore a little bit about what it means to change the oxidation number, how we determine oxidation numbers, and then how they're going to change with oxidation or reduction reactions. So increases in oxidation number, meaning you become more positive, happens if something loses electrons. And then you're going to see a decrease in oxidation number. Something becomes more negative as it gains electrons. And that's a little bit confusing sometimes for people to understand because they think about how can gaining something make me move more positive along a number line. But remember, we're gaining things that are negatively charged. So that's why we have this decrease in oxidation number becoming more negative. So if that's not clear right now, hopefully as we do an example, it will become a little bit more clear. So some terminology that can be confusing, but you want to make sure that you understand it well because lots of the multiple choice questions or some of the simple skill questions might involve asking who's oxidized, who's reduced, who's the oxidizing agent, who's the reducing agent. So again, oxidation reactions are not going to occur. Somebody's not going to lose electrons unless there's somebody there to gain them, somebody to be reduced. So that's why we call these oxidation reduction reactions, that word together. Sometimes they're referred to as redox reactions. One doesn't happen without the other. So two terms to kind of think about that we will see are reducing agents and then oxidizing agents. So if you just want to remember that it's sort of the opposite, a reducing agent is something that's oxidized, an oxidizing agent is something that's reduced, you can just memorize that. But if you think about it, it should make some sense. A reducing agent is somebody who's forcing someone else to be reduced. They're forcing someone else to gain electrons, and that's because they're giving up their own electrons. So that's a reducing agent. An oxidizing agent, that's forcing someone to be oxidized. They're an agent of oxidation. So they're going to force someone else to lose their electrons so they can gain them. They're going to be reduced. So however you want to remember it, it is an important skill that we're familiar kind of with this nomenclature. All right, so the big meaty part of this skill is really thinking about how we assign and then use oxidation numbers. So an oxidation number, which we'll abbreviate ON, really refers to what we call the oxidation state. And you can imagine this if we were to imagine that an atom were to completely transfer its electrons, not necessarily share them, but if we were to imagine it was part of an ionic compound, what would the charge on it be? And so the periodic table is again going to be our best cheat sheet. So if we look at here and some of the columns that we're familiar with, things that are in group 1A or 2A, they're going to be +1 or +2 in terms of their oxidation numbers. Those oxidation numbers are going to be the same as the charge. For things that fall in group 7, like the halogens, right, we're going to be -1. For oxygen or anything that's kind of in that column, it's going to generally be -2, but the one kind of trick one that we have to look out for is if we have a peroxide. If we have a peroxide, then that oxygen is going to be -1. So you have to make sure to look out for things that are peroxides, whether it's in the name or if you see it like hydrogen peroxide. Hydrogen peroxide is H2O2. Okay. Couple of other rules to think about, and then we're going to run through an example here. Anything that's in its elemental form, if something is as you find it on the periodic table, they're going to be neutrally charged because they're elements in their elemental form. The oxidation number is 0. Again, if we have ions, this kind of follows into this camp here, but if we have monatomic ions, the oxidation number is just going to be whatever the charge is on that ion. And this is going to become important. We'll see that in our example. If we have, for example, a polyatomic ion, we can figure out oxidation numbers for each of the individual atoms that are in there, but the overall oxidation numbers and then the numbers of each element we have, at the end of the day, we have to add up to the ion's charge. This will probably make more sense as we walk through an example. So this is the rules that we have for assigning oxidation number. This is not something that's provided for you. Largely, this is just information that we could get from our best cheat sheet, our periodic table, but some things that aren't necessarily written on the periodic table. Things in their elemental form will have an oxidation number of 0, and when we're considering polyatomic ions, we need to make sure that the sum total of the oxidation numbers equals the total charge on the ion. So that'll make sense here as we go through an example. So one of the things that you're going to have to do as a skill is you're going to look at an equation, you're going to look at a reaction, and you're going to need to identify who is being oxidized, who's being reduced, who's the oxidizing agent, the reducing agent, those terminologies. And so we're going to go through this 4-step process. I'm going to go through an example problem here with you, how we assign oxidation numbers to all reactions. We're going to use tie lines to actually identify changes in oxidation number. And then we're going to use those changes in oxidation number to identify things that are oxidation steps, where we're going to have an increase in oxidation number because we've lost electrons, or a reduction step, where we're going to have a decrease in oxidation number because we've had a gain of electrons. So the best way to probably highlight this is to just go through an example. We've got potassium nitrate as a solid is going to be converted to potassium oxide, nitrogen gas at potassium oxide is a solid, nitrogen gas, and then oxygen gas. So again, this could be one of those embedded skills problems where maybe we're only given chemical names. And we have to translate that to a chemical formula. We have to take those words and make them into a chemical equation. Then we have to actually balance the chemical equation. This one is a little bit more involved in terms of balancing. We're going to have a 4, a 2, a 2, and a 5. But I want to make sure to highlight here that these coefficients, even though they're important for a balanced chemical equation, these coefficients do not affect oxidation number. So important for a balanced chemical equation, important if we needed to do stoichiometry, but they do not affect anything to do with assigning oxidation numbers. All right, so let's figure out how we assign oxidation numbers. Well, potassium here is going to be +1 because that's what it would be, as its monatomic ion. We're going to take the nitrate piece here, and we need to break this apart separately. So I'm going to bring nitrate down here just to work on it separately. So nitrate as NO3 is a -1 charge. So one of the things that we have to do is we have to have everything at the end add up to -1. All right, so what we need to do now is treat the nitrogen and the oxygen separately. Oftentimes, oxygen is one that's easy to start with because unless it's part of a peroxide, we know it's going to be -2. Now watch what happens here. The oxidation number on oxygen is -2, but because we have 3 of them, that contributes a -6 to the overall charge. If I know that the overall charge on my ion is -1, hopefully it makes sense that the contribution of charge from my nitrogen is +5. Since there's only one nitrogen atom, that must mean that the oxidation number on that nitrogen is +5. Okay? I would encourage you go through and practice this with a few other polyatomic ions. Practice identifying those oxidation numbers on those individual species. So I'm going to come here and it's a +5 for my nitrogen and it's a -2 for that oxygen. Those are the oxidation numbers. I'm not going to put a -6 for that oxygen as its oxidation number. Each oxygen contributes a -2, and there's 3 of them. So just make sure we know that that oxidation number is per oxygen atom. Let's move over to the right side when we've got potassium oxide here. That oxygen is always -2, potassium is +1. That one's pretty straightforward. And these last two, remember, if we have something that's in its elemental form, when we find non-metals like nitrogen and oxygen, any of the halogens as gases, we are going to see them as diatomic gases. Okay, so they're going to be in their elemental form here. Any metals, if we had a metal that was just a metal as a solid that's in its elemental form, oxidation numbers are 0. So now what we need to do is we need to connect species that are the same atom but change their oxidation number. So looking through here, we can see potassium doesn't change its oxidation number, so potassium is not undergoing any redox chemistry. The same with oxygen. Actually, that's the only one that's not changing is potassium here. Sorry about that. Oxygen is changing. We can tie oxygen over here to oxygen here. Now, I wouldn't want to tie it to this guy. This is the one I was looking at first. We don't see any change there. So that's not where the change is happening with oxygen. The change is happening with oxygen as it's made into elemental oxygen. Okay? So one of the things we want to realize here is as we go from -2 to 0, that's losing electrons. And I know it's a little bit weird to think of going from negative to 0 means you're losing things, but we've lost negative things, okay? So we're going to see an increase in oxidation number with a loss of electrons, and a loss of electrons is oxidation. I'm going to just move my stuff down here just a little bit so that I'm not writing over my words there. Okay, so we're going to tie those 2 oxygen atoms together that are changing in oxidation number. Okay, we said potassium wasn't changing, but we can see that nitrogen is. In this case, we are decreasing our oxidation number. Okay, we're going from a +5 to a 0. A decrease in oxidation number means we're gaining electrons. And I know, again, this is strange. We go from +5 to 0. That actually means we gain something. I know it seems like you're losing something, but we're gaining negative things. That's why we're decreasing our oxidation number, is because we're gaining electrons. Gaining electrons is reduction. So gaining electrons is reduction. So now we've gone and identifying who's being oxidized. The nitrate and the oxygen and nitrate is being oxidized, and then the nitrogen in nitrate is being reduced. So notice here, we can't even say that nitrate is being oxidized or reduced because the elements within nitrate, that oxygen is being oxidized and then the nitrogen is being reduced. Okay, so usually when you're identifying who's being oxidized or being reduced, you're identifying a specific element. So if we wanted to identify and answer questions here, we'd say that oxygen is being oxidized, which means it's the reducing agent, and then nitrogen is being reduced, which means it's the oxidizing agent. So a lot of terminology there, but using these redox reactions and using kind of these oxidation numbers is going to be a key skill to learn moving forward. Last thing here is thinking about types of redox reactions. So I'm just going to give some examples here. One of the skills you might have to do is you'll see a chemical reaction, and then you're going to have to identify Is it one of these 4 possible kinds of redox reactions? The first kind that we're going to see is called a combination reaction. Big thing here, you want to know if a redox reaction is going on, look to see if you have things in their elemental form. If you have things in their elemental form on one side of a reaction, they're probably not in their elemental form on the other side. That's a good clue that something's going on. But again, being able to understand and name the kind of chemistry is going to become important. So a combination reaction, like the name implies, you have 2 or more reactants, at least one of them must be an element in its pure form. They're going to combine to form a new compound. So here, let me just give you an example here. If we had 3 magnesium plus nitrogen gas, that could generate magnesium nitride, Mg3N2, as a solid. In this case, both of the species happen to be things that were in their elemental form. Just running really briefly through, right? Oxidation numbers of 0 on both of those guys, and then it's going to be +2 and -3 for those species in that ionic compound. So absolutely see that we're changing oxidation number. Decomposition reactions. Here's an example of a decomposition reaction. Water, and again, or I'm sorry, this is peroxide I wanted to do here. Peroxide is going to be breaking down to water plus oxygen gas. We're going to have a 2 in front of there to balance it. So notice here again what we have is we look and we can see, oh, we've got oxygen in its elemental form and oxygen in its peroxide form. So remember, that's going to have a -1. But even if you had that wrong and you had the wrong, even though this is -1, if you identified the oxidation number as -2, which would be incorrect, but you still should see that we're doing some chemistry to change that oxidation number to be 0. So this is a decomposition reaction. Like the name kind of implies, we start with a single compound and we decompose or break it down into at least one other product that is a pure element. So we're going to have, again, that change in oxidation number. Another example here of a displacement reaction. We're going to see a single displacement reaction. Let me give an example here. If we had 2 aluminum plus 3 lead nitrate, generating 2 aluminum nitrate plus 3 lead in its elemental form. So it's kind of like we're swapping out who gets to be in their elemental form. On the left side, we've got aluminum in its elemental form, where it's an ion on the right. On the left, we've got lead in its ionic form and now in its elemental form. So we're kind of swapping and displacing who gets to be in their elemental form. If you actually go back and look at, for example, any of the acid-base reactions, or you look at some of the precipitation reactions, none of those change oxidation numbers, but those are what we call double displacement. Remember, we were swapping who was partners with who? That's called a double displacement reaction. Single displacement is we're going to be swapping somebody out with an element. All right, the last kind of reaction that we've already talked about in a couple of other learning units here are combustion reactions. I'm just going to give a generic combustion reaction that we see here, for example, with methane gas. That's what's used to, heat your furnace and so forth. Balancing this equation requires a little bit more effort than maybe some of our other equations, but combustion reactions always take and combine a fuel with oxygen, and we generate carbon dioxide and water. So a combustion reaction, again, looking at what we have here, we're going to have oxygen in its elemental form here. And then in both of these species, oxygen is going to have a -2 oxidation number. So going from 0 to -2 meant we are going to be reducing oxygen. So we reduce oxygen in both the formation of carbon dioxide and water. And in this case, that carbon atom is actually going to be oxidized as we go and we form carbon dioxide. Okay, so that is our redox kind of reactions. And that sums up the last skill for our fourth learning unit on kinds of aqueous chemistry. Now, a lot of this chemistry that we see with redox might not necessarily be in aqueous chemistry, but some of it will be.